Once we have discussed the how we can model a game as a tree, we want to discuss the branching factor of the tree. See, this is the tic-tac-toe game's tree. So here the initial state where the board is empty and the first person who plays X starts playing, that person can place X in any of the 9 spots. Okay, so this will have 9 children in total at this stage, the first stage. So once the first person has put X in one of the 9 available spots, how many spots are left for the second person? For the second person, there will be only 8 spots left to put a circle. So for the second level, for each of those 9 first level children, there will be 8 other second level children for the second player. Now the third level, again the first player will play, right? It's a turn taking. How many positions to place X for that person? For every second level node, there will be 7 different spots because 2 spots are already taken. In that way, total there are 9 different slots. So there will be 9 levels in the tree. Let's see how it works. The branching factor refers to the number of possible legal moves a player can make at each turn. And we discussed about the number of legal moves. Initially 9 for the first player. At the second level, for each first node, 8 different positions for the second player, and so on and so forth. So that's what it said there. At the start, there are 9 possible moves. After X moves, there are 8 legal moves left, then 7, and so on. So the average branching factor in tic-tac-toe is like at the first level 9, second level 8, third level 7. In that way, and we divide by total, 9 different positions. So around 5. So average number of children at each level is around 5. Okay. So total number of nodes in this tree will be 9 factorial, which is 362, 360, 880. So this is a lot of nodes. You cannot draw the whole tree. And this is a very small game, tic-tac-toe. And AI needs to analyze all the states and find out the best states, right? So this is very important to do that. So now, in the game tree, we have what we are seeing. The game tree has nodes as game states. The nodes are basically nothing but game states, right? The ages are the moves. When you take an action, make a move, that's the ages. And the terminal nodes are the outcomes, right? The outcomes are always at the terminal nodes, the last node. So you have no idea of the utility value anywhere in the middle. Please understand. So like in the Romania map problem, we are saying, okay, we take a step and we are going from Arad to Sibiu and the path length is 140 miles, let's say. But here in this game tree, we have no idea at any intermediate stage what is the utility value until we reach the last state, the terminal state or the leaf node in the tree. And the leaf node's depth can be different, right? If it's a draw, we go to probably the 9, all 9 boxes are full. But if, like we have seen in the previous example, like after 5, 6, or 7 moves, you can reach a win or lose situation, right? So terminal nodes are basically the outcomes. We have to understand that, okay? And tic-tac-toe, as I said, the initial empty board gives the max. That means the player, we sometimes call the player who is playing the X as max because he's trying to maximize his own utility. And the player which playing circle or 0 or whatever you say as min, because the idea is not that he wants to minimize his profit. The idea is that he wants to minimize the outcome of the opponent because it's an adversarial game. It wants to minimize the utility or outcome of the opponent. Remember that, okay? So this is very important. So let's move on. And now we want to see the branching factor for another 2-person turn-taking game, which is chess. Right? So what do you think about chess? This is more difficult. Okay, chess is more difficult. In chess, the branching factor varies depending on the position, right? Opening moves have fewer possibilities, while mid-game moves have much more. And again, at the end game, you have less. So let's see. In opening position, there are typically 20 legal moves, okay? Like 8 pawns can move forward 1 or 2 square. And 2 knights can move to 2 places each. So that's around 20 legal moves. In mid-game, the number of legal moves increases due to more developed pieces, reaching 30 to 40 moves per position on average. Because there's so many pieces for both sides. In end game, the number of legal moves typically decreases as pieces are captured, and there are not as many pieces, okay? So now you see, averaging over the whole game, we, across all positions in a typical chess game, we find the average number of legal moves per position is around 35. Around 35, okay? So now let's see the size of the game tree, okay? So game tree size for 35 possible moves on average, and games typically last 40 moves per player, right? The white plays 40 moves, the black plays 40 moves. So total there are 40 plus 40, 80 moves. So we can have a total of 35 to the power 80, which amounts to around 3.35 times 10 to the power 122, or around 10 to the power 123 possible game states, which is this large number. Like 3 undecillion, 353 decillion, 77 nonillion, and going up to 625 billion, 923 million, 370,000, 388,228, which is a astronomically large number, and no real world computational environment can evaluate this game tree. You can understand, right? So we cannot explore the entire tree. That's the basic idea. So what is the key takeaway? We can model adversarial games, two-person, turn-taking, zero-sum as trees. We can evaluate the branching factors, but after we evaluate the branching factor, the average number of state moves, we can calculate like the total number of, roughly the total number of states in the tree, or the total number of nodes. But then we see how we evaluate that tree, how we know which is the optimal move, the optimal path. So we cannot explore this entire tree. So the key takeaway is adversarial search transforms games into structured search problems. It's again a search problem, but our existing search algorithm will not be able to analyze it. But because full exploration is impossible in large games, we need smarter strategies like minimax for optimal play, alpha beta pruning for efficiency, and heuristic evaluation function when time runs out.